morning, everybody, and welcome to this session. I just wanted to I'm Nikki Pronto from Nothing, so I just wanted to give a couple introductory remarks to provide some context for today's session. So on Tuesday, you heard about the beautiful richness and diversity of life and everything that life produces and does. But today we're going to zoom out a little bit and focus on what's remotely detectable. And this is a graphic, a cartoon that Vicki showed on Monday. So to link it to her great overview talk, we've addressed in a general sense what does life produce. But again, today and tomorrow, you're going to be hearing more about remotely detectable biosignatures. And then we're also going to move into asking the question, can a dead planet fool us? Because putative biosignature detection is still a couple of steps away from life detection. And as Vicki pointed out, you have to interpret the biosignatures within the context of the environment and consider things such as false positives and false negatives. I also wanted to point out some really great references, in particular Eddie Schwederman's review article on exoplanet biosignatures. So that's available online. And so to start, I'm very pleased to introduce Stephanie Olson, who's going to be talking about distinguishing biologic from geologic methane.
Good morning, everyone. I have been given the very daunting task of discussing the potential usefulness of methane as an exoplanet biosignature. And what this comes down to is really addressing the question of whether or not we can ever hope to distinguish biologically produced methane from methane that is geologically produced instead. And so earlier this week, we had two really great talks, one by Jen Glass and one by Diane Newman, that explored the methane cycle here on Earth. And so I'm not going to reiterate too much of what they said, but there are two key points that you should remember. First is that the methane in our atmosphere is overwhelmingly biological in origin. And so life is producing lots of methane compared to geology here at present. And the second is that methanogenesis is a very simple metabolism shown here. It's just the reduction of CO2 by hydrogen. And so it's a very ancient metabolism here on Earth. There is some debate regarding the exact timing of the emergence of methanogenesis, but it is fair to say that life has been making huge volumes of methane on Earth for the vast majority of our planet's history. And so the element that I would like to add to that story is just to point out that I think methanogenesis is likely to be a viable metabolism on other habitable planets as well. And that's because it depends on substrates that we expect to find on other habitable planets. Methanogenesis is using hydrogen, which is extremely common in the universe. And it depends on CO2, which we think is a key ingredient for long-term habitability because it participates in weathering feedbacks that help to regulate surface temperature. But of course, the key problem here is that geological sources of methane do exist as well. Now, Jen told us that all of these sources of methane are pretty small on the present-day Earth, and that is true. But you might also remember that Kevin Zonley talked about how we can get pulses of methane arising from impacts on the very early Earth. And as we move to exoplanets that might be more reducing than our own planet, this assumption that the volcanic source of methane will be small becomes less valid. And so we could potentially be encountering more geological methane elsewhere. A further complication is that the stellar spectrum really matters for this problem. This is something that Vicki Meadows talked about on Monday. And the issue is that around some types of stars, the UV environment may be more favorable to methane accumulation than our own star. And so equivalently small methane fluxes might yield very different methane abundances in exoplanet atmospheres. And so when it comes to leveraging methane as an exoplanet biosignature, our goal really needs to be quantifying what the surface flux is rather than relying on abundances alone, because we may be misled in that case. And so what I'm going to do now is walk through 3 different strategies that might potentially help us cope with the ambiguities that are inherent to a methane detection. And then I'll return to each of those 3 strategies in greater detail later. So just as we need to place our planet in the stellar context, we need to interpret atmospheric methane in the broader chemical context of the exoplanet's atmosphere. And in particular, that involves looking for combinations of gases that you wouldn't expect to coexist at thermodynamic equilibrium. So as an example here, I'm showing a photo of my cat and my dog. And if my cat had his way, these 2 would never coexist. And some gases are exactly like that. And so that's the sort of thing we should be looking for. The next thing we could do is look for things that are known as false positive indicators, or red flags that we might be looking at geological rather than biological methane. And so those of you who are skilled in the art of online dating will know that it's insufficient to vet potential candidate matches in terms of their desirable characteristics alone. You also need to vet them for their undesirable traits and to look for red flags. So in this example here, Betsy and Doug are both very, very attractive. Either would fulfill all your methane needs. But I think most of us in this room would swipe left on Doug because his apparent beliefs regarding the geometry of our planet represent a very major red flag. Okay, the next thing that we could do is literally just check back later and look for seasonality. Now, this is a phenomenon that the local attendees might not be familiar with, and so I have provided an example here. This is the view from my Chicago apartment on a beautiful day in June, and this is the exact same view just a few months later in January. And there's a 100 degrees difference between these 2 photos. And so nearly every aspect of the physical environment has changed. And these changes in the environment can drive changes in biological activity and in the rates of atmospheric reactions that may manifest as seasonality in atmospheric composition. And so if we're hoping to recognize life based on its impact on atmospheric composition, I think it's essential that we understand the potential for seasonality. And in particular, I think it's important that we look many times because if we depend on a single observation, we might draw very different conclusions regarding the existence of life. So as I've said, these 3 strategies will form the remainder of my talk. And I'm going to keep the discussion largely conceptual and qualitative. And that's because Josh Christensen-Totten is going to return to these first 2 in much greater detail. I'd like to note that it was his idea to slide up from the bottom. I'd also request that you save your most difficult questions for him. Okay, so again, disequilibrium is the coexistence of incompatible species. In my own life, that is my cat and my dog, who only coexist because I foolishly thought that having both of them in an apartment was a good idea. But in the context of exoplanet life detection, when people refer to disequilibrium, they're typically talking about the coexistence of methane and oxygen. So this is potentially a biosignature because you would not expect high levels of methane to coexist with high levels of oxygen in the absence of large surface fluxes, because these 2 are mutual reactants in a very energetically favorable reaction. You might recognize this reaction as natural gas combustion. And so if we were to find high levels of both gases, the implication there would be that both gases are being supplied to the atmosphere at relatively large rates, large enough rates that maybe biology is the only reasonable explanation. Of course, the problem is that this does not actually work for recognizing life on a true Earth twin. So this is something that Tim Lyons talked about on Monday. We have a very well oxygenated atmosphere today, but methane's pretty low. We've had intervals of Earth's history where we think we had much higher levels of methane, but of course, at those times, oxygen was low, and ultimately, we don't think that either of these gases have overlapping detectabilities in the history of our own planet. And so although I would not doubt the interpretation of oxygen-methane disequilibrium if we were lucky enough to find it, I am a little pessimistic about the likelihood that we actually would. Fortunately, atmospheric disequilibrium doesn't always have to be so dramatic as the coexistence of oxygen and methane. It can be a bit more subtle. So as it turns out, the coexistence of methane and carbon dioxide represents a very significant disequilibrium. And that's because methane represents carbon in its most reduced form, and CO2 represents carbon in its most oxidized form. The two species are separated by 8 electrons, which is actually pretty huge in redox space. And so although geological sources of both gases certainly exist, and neither is uniquely biological, coexistence of high levels of both gases is unlikely in the absence of life because one of these species should be overwhelmingly favored by the ambient conditions on a habitable planet. And so if you saw both, you should be suspicious. This is something that Josh will return to in much greater detail. Now, this is a bit more speculative, but disequilibrium need not refer to the bulk composition of an atmosphere. It could also refer to isotopic disequilibrium. This is, of course, an exceptionally challenging measurement to make, and we are not currently equipped to do so. Probably won't be in the near future. But nonetheless, if we found CO2 and methane coexisting in an atmosphere, a secondary check on whether or not that is likely to be a biological signal would be to look at the isotopes. Life on Earth has strong preferences for like carbon isotopes. And so we might expect that if this is a biological signal, the carbon dioxide and the methane would be isotopically very different. And if they were not, that might be a red flag that we're not actually looking at life. Perhaps this is a geological phenomenon that we haven't considered yet. So on the topic of red flags, I'd like to continue with some more. All right, I've already told you that you can get potentially significant methane from volcanoes on planets that are more reducing than our own. But fortunately, volcanoes that are making methane aren't just making methane. They also produce other gases as well. And so in this case, we might recognize that we're looking at geological methane by looking for those other gases, gases like carbon monoxide, which tends to accompany geological methane. And so that would be a red flag, and in this case, a false positive indicator. But it's important to note that having geological methane does not preclude the possibility of also having biological methane. And it definitely does not mean that the planet is sterile, even in the face of this false positive. And so you need to be careful about jumping to conclusions based on red flags. A further complication here is, again, that the stellar spectrum really matters, as Vicki told us on Monday. And that's because some stars will have UV environments that are more conducive to photochemical buildup of carbon monoxide from methane photolysis in atmospheres. In this case, photochemical carbon monoxide says nothing about the source of methane on that planet. The methane could be biological or it could be geological. And so carbon monoxide is not always a red flag for methane biosignatures. Okay, while we're on the topic of red flags, there are a couple of additional types of red flags to talk about. They're not unique to methane, but I've included them nonetheless. The first is this concept of anti-biosignatures, which are evidence for the absence of life on a planet that seems to meet our criteria for habitability. And so some of you might be aware that the classical example of a anti-biosignature is actually carbon monoxide. But it turns out that that's actually just fatally flawed. The logic was that carbon monoxide is such a tasty molecule. It's an excellent carbon substrate and an energy source on both reducing and oxidizing planets. And so if there were life around, it should eat up all the carbon monoxide. And a carbon monoxide-rich atmosphere is just simply incompatible with the existence of life. This is a problem, though, for a couple of reasons. Yesterday, Hilary Hartnett told us that life is neither carbon nor energy limited. It's in fact limited by nutrients. And so there are many reasons why life might not completely draw down atmospheric carbon monoxide on an inhabited planet. And so carbon monoxide can be compatible with life. And the bigger problem for carbon monoxide as an anti-biosignature is that life on Earth actually makes more carbon monoxide than it consumes. Our biosphere is a net source of carbon monoxide. And so what this means is that in some circumstances, carbon monoxide can actually be a biosignature rather than an anti-biosignature. And so we're now learning that this idea of anti-biosignatures is just as complicated and nuanced as biosignatures themselves. And unfortunately, we don't have any smoking gun examples of what an anti-biosignature might be. And so this is a problem that'll need to be addressed moving forward. The second type of red flag is much more straightforward. These are habitability precluders, or evidence that a planet is not actually capable of supporting life as we know it. So this could be evidence for the absence of water on a planet, perhaps due to catastrophic hydrogen escape. Okay, now I will move on to the final section of my talk, which is exploring seasonality, which can be thought of as the pulse of a biosphere. So this is a phenomenon that is best expressed in the abundance of atmospheric CO2. Here I'm showing CO2 levels measured at Mauna Loa Observatory in Hawaii. And of course, the most notable feature of this figure is the long-term average increase in CO2 levels due to the burning of fossil fuels. But then superimposed on that, there is a beautiful seasonal cycle. So now I'm showing the same data, just detrended to highlight that seasonal signal. And what's going on here is that CO2 is rising and falling throughout the year due to seasonal shifts in the balance of photosynthesis, which draws down CO2 and dominates in the warm, sunny months, and respiration, which releases CO2 back to the atmosphere and dominates in the dark, cold winter months. And so the idea is that if we were to observe similar seasonality on an exoplanet, we might be able to infer the presence of life based on the signal, despite the fact that CO2 isn't really a biosignature by itself, but its variability would be. Now, methane oscillates seasonally as well. But unlike CO2, which oscillated seasonally in response to seasonality and biological activity, this signal is actually photochemical in origin. What's happening is that during the warm summer months, there is more evaporation, leading to more water vapor in our atmosphere, and thus more water vapor photolysis and the production of hydroxyl radicals. What this means is that the atmosphere in the summer months is actually more oxidizing than it is in the winter months, and methane destruction is enhanced. And so methane levels decline throughout the summer. But very importantly, the recovery of methane every winter requires that there is a large and active source of methane from our planet's surface. And so even though this is a photochemical signal, methane seasonality is still informative in the context of exoplanets because what it tells you is that the methane source is active and ongoing. You're not looking at methane delivered from a stochastic event like the ones that Kevin was talking about on Monday. And so this would lend a bit more confidence to a biological interpretation for methane. The other point here is that this seasonal cycle is mechanistically linked to our hydrologic cycle. And so this is actually a habitability indicator for that reason. And so even though, again, an abiotic signal, this does provide information about a planet's ability to support life. Okay, so to summarize everything that I have just said, methane as a biosignature is really hard. Simply identifying methane will not be enough to convince ourselves that we have found life. Ideally, that methane should be coexisting with an oxidized species like CO2 or oxygen or ozone, its photochemical product, which might be more detectable than oxygen itself. And in the best case scenario, at least one of these species should be varying in time. And all the while, we need to be mindful of red flags. So ideally, we wouldn't see carbon monoxide if we were looking at a planet orbiting a sun-like star. And we need to understand how our interpretation of carbon monoxide might differ if we were looking at an M star, for example. And so, again, the stellar spectrum is important there. Okay, so this slide basically says the exact same thing in words on the left and pictures on the right. And so hopefully at least one of these means something to you. But to recap again very briefly, if we want to leverage methane as a biosignature, we need to first characterize the stellar context, and that is because that is what allows us to translate between abundance and flux, right? And that's an important distinction. What we want is disequilibrium and absence of red flags, and ideally, our wish list includes things like seasonality, and potentially in the distant future, things like isotopes. And so with that, I will thank you for your attention.
So possibly I missed this, but what would be a good red flag for M-dwarfs if it's not CO?
Well, a really oxygen-dense atmosphere would be undesirable if it's a reflection of water loss. A very oxidizing environment also would not be favorable to the origin of life as we understand it. So I would consider that a red flag.
For exoplanets, do we have a good way of measuring isotopes? What's the best way of measuring isotopes?
We cannot currently measure isotopes. That is a dream, but they have slightly different masses, so they have slightly different features, and so we just need a really spectacular telescope. Yes, Megan. Mm-hmm.
Is there a good way to tell whether seasonality would be biological based or geological based, something like evaporation of ice versus, like plants making more like CO2 or something like that?
So the expectation is that CO2 seasonality won't, I should rewind. We have CO2 seasonality on Mars due to this process that you're describing, seasonal sublimation and condensation of CO2 ices. However, that process is occurring at temperatures that we don't expect to find on habitable planets. And so I don't expect significant abiotic CO2 seasonality on a habitable planet, although we might find it elsewhere.
Sorry, I just wanted to make a quick comment on the isotope detectability. You're right, we can do it now. I did talk about the ACO potentially, but that's not biologically mediated. But just to let people know, there are isotope bands in the mid-infrared for carbon dioxide that actually produce pretty strong features. And we would need a future telescope, preferably one that is an interferometer observing the mid-infrared, but don't give up whole hope because there's the possibility of being able to observe those bands. Maybe, I don't know, 20, 30, 40, 50 years from now.
Great, thank you.
Concerning the seasonality signal, if you were to look at an exoplanet globally rather than these local measurements, do you require a significant hemispheric asymmetry for the signal to show up?
So on Earth, we do, on global average, have a seasonal signal due to hemispheric asymmetry. And so that'll be helpful. However, it is not necessary because it's important to remember that when we're viewing an exoplanet, the disk average that we see will not necessarily be the global average. And in fact, it's just as likely that we have a view that is dominated by one hemisphere as the scenario where we have equally contributing hemispheres. And so it's a geometric concern, but the asymmetry is not strictly required.
We have time, there's a couple more minutes for questions. I'll just go ahead and ask you, have you thought about methane on Mars?
Oh, no. No. I would rather not comment on the abundance or variability in either space or time of methane on Mars. Yeah. Yeah. I hear Kevin has some strong thoughts about that, though. It's something that we should think about and attempt to model in the context of the stellar spectrum. I will say that on Archean Earth, biological carbon monoxide fluxes would have been much larger, and we expect much greater accumulation of carbon monoxide under those conditions. Eddie Schwieterman recently had a paper exploring the potential for carbon monoxide accumulation in the presence of life on planets orbiting both sun-like stars and M stars, and we did find that relatively high levels of carbon monoxide are possible and compatible with life.
Well, let's go ahead and thank